Welcome back from lunch, everybody. My name is Yusra AlSayyad. I coordinate for the Data Management Science Pipelines. And it seems like we've been doing better since the pandemic on being kind to each other. Let's see if we can keep up the good work. I believe in you. Remember that this is hybrid. We have Tris, who will be monitoring the Slack channel for this session, and Agnes, who's going to be monitoring the Zoom chat for this session. We have, so every year at the PCW, since the algorithms workshop, I've given an update on the status of the science pipelines. While the status changes every year, the plans that we presented in the algorithms workshop are all still current. So if there's any algorithm where you want more detail, you want to find out exactly what we have planned, please go to ls.st/law, find the topic that you're interested in, and watch the video from those. I promise they're still current. We are going to format this talk today as a 60-minute tag team scientific release notes about the current performance of the pipelines. We have a number of people from the Science Pipelines team in person. This is a smaller group than in previous years because as of 3 months ago when we were registering for this meeting, we thought we were going to be on Sky with ComCam right now. A couple people I want to highlight. A couple people I want to highlight who are in person: Eli Reichhoff, our calibration scientist; Robert Lupton, our former pipeline scientist. And on Zoom, we have Jim Bosch, our current pipeline scientist and our science lead for the data release production pipeline, and Eric Bellum, the alert production scientist. We also have a number of pipelines folks on Zoom who are available to answer questions that come up in the panel discussion. So the plan is we'll do 60-minute tag team talk, and then we'll do 30 minutes of Q&A, and there's a number of pipelines folks here to answer questions, and we can direct the question to the person who works on that particular algorithm. Since last year, we've had 2 pipelines folks join. Please welcome Pierre-Francois and Alex Broughton. You'll hear from Pierre-Francois on PSF modeling today. And remember, so I'm going to be speaking today on behalf of the whole Science Pipelines team. Anytime, so this presentation, as always, is a group effort. The slides were made by a number of people. Anytime the person who made the slides or is responsible for that particular algorithm isn't speaking to them, you'll see their photo in the bottom right-hand corner. Even if they're not on Zoom today and available to take questions, they welcome questions on Slack anytime. We are scientists first, just like you. We are really excited about the science that we're going to do with LSST. We are all members of a science collaboration. We're all embedded in a physics or astronomy department, usually at UW, Princeton, or here. And we are contributing to LSST by writing the image processing algorithms that will take the raw images coming off the telescope, calibrating out the effects of the atmosphere and the instrument to produce science-ready images and catalogs. While we expect that a lot of science you'll be able to do with catalogs alone, we know that you're going to develop novel image processing algorithms. And that is why the processed visit images, the difference images, and the coads are all first-class data products for you to run your shift and stack detection algorithms or detect your ultra diffuse galaxies. While we will be honored if you would run your new image processing algorithms on these images for years to come, we are committed to making it possible to do so with these particular images, our PSF models. You should not have to redo instrument signature removal, for example. We are also committed to providing state-of-the-art algorithms through operations, regardless of what the construction requirements say. The state-of-the-art in wide field image processing algorithms has changed a lot over the last 10 years. And we believe that we have tracked that state of the art well. And in the cases where there is a gap where we are not at state of the art, we are actively implementing those algorithms right now. For example, the extended PSFs from bright stars, cell-based coads, and things like that. How can I be so confident in the pipeline performance if we're not on Sky with LSST CAM yet? We've been running on precursor data sets for years. And I want to spend some time to go through these precursor data sets because the scientific performance plots that we're going to show in the second half of this talk are all based on these particular data sets. We use simulated data and real data from current wide field surveys. For simulated data, we use DESC's DC2 Run 2.2i. And the newest addition this year is simulations of ComCam. Simulations are good when you need a truth catalog or the specific LSST camera geometry or our specific survey strategy, but it doesn't have the gory realities that real data has. For those, we use DCAM and HyperSuPrimeCam. DCAM is useful because it doesn't have an atmospheric dispersion corrector, just like LSST won't. And HSC is useful because it goes deep, really deep, as deep as we expect from LSST. We also have a very special relationship with the two cosmological surveys that are running on those cameras. For DES in particular, there's a lot of overlap in the actual humans that are developing the algorithms for that. For example, Eli and Josh Myers. And DES has been pushing state of the art for years now. And we have learned a lot from that data set and in many cases have adopted the algorithms that were developed for DES. Our special relationship with HSC is that the LSST Science Pipelines are the pipelines that were used to do the data releases for the Subaru strategic program. And there's nothing been more useful feedback than getting feedback from real scientists that are trying to write papers with your data products. Finally, since the pandemic, we've been using Oxtel's Lattice. Remember, Lattice was installed primarily to be a spectrograph for measuring the atmospheric transmission above Rubin Observatory, but you can also run it as an imager. And it's been streaming images since the pandemic. And this has been incredible for measuring, for the end-to-end, testing the end-to-end system of data management. For science pipelines in particular, it's been useful because it's a real ITL chip, just like you'll find on the LSST focal plane. And we've been able to refine the instrument signature removal using Lattice over the years. So when I say we've been running pipelines on these precursor data sets for years, what do I mean? Pipelines are made up of tasks. Tasks are the building blocks of pipelines. And these building blocks are various algorithms. And these algorithms can be built into different pipelines. And these pipelines come in 3 different flavors. There's the alert production pipeline, which supports science that requires rapid follow-up, the data release production pipeline, which supports static sky science and statistical studies of variability, and the calibration production pipeline, which produces the calibration frames, does the daily camera health check. All the pipelines share the same algorithmic components, and we have roughly 3 groups within Science Pipelines that focus their effort on one of these 3 pipelines. But all of us, we are all within Science Pipelines, we are all in data management. So I've heard like a couple misconceptions this meeting that some of these groups are separate from data management. We all own the whole code base, the whole stack. Some of these tasks are not image processing algorithms, but serve only to perform some kind of QA or assess scientific performance of the pipelines. So we'll go through some of those examples in a second. If you ever want to get a copy of the real pipeline graph, We have some pre-rendered full versions of this at this website here. We have plans to move this to pipelines to lsst.io. But for now, you'll be able to see the current version of all 3 flavors of pipelines at this website. So a couple years ago, we advertised that we had added a task whose job it was to produce HIPS maps. These are pre-rendered hierarchical tilings of the sky that let you zoom and pan in a HIPS viewer. We made one of these for DP 0.2, for example. In the past year, Nate Lust has made some improvements to the color and brightness scaling, and you should see updated versions of this in our data products soon. Most of our QA tasks are in analysis tools and produce plots and metrics. And I'm going to go through this in a little bit of detail because you're going to be seeing a lot of these plots and metrics in the assessment of these algorithms later in this talk. So this particular example is a plot that appears in analysis tools. And if you plot G minus R versus R minus I of isolated point sources, they collapse into a so-called stellar locus. The width it has an intrinsic width due to the variance in the metallicity, but any width beyond that is due to uncertainty or problems with your algorithms. And it could be any algorithms can contribute to this width. It could be your PSF modeling, your astrometry, your photometry. And in this way, it serves as a very high level, one of our highest level metrics to alert us of problems if they appear. Another one of these high level metrics that we use, for example, is the number of DIA sources. You can get an increase in false positives in your difference images if there's a problem with any of your algorithms, whether it be astrometry, PSF modeling, background estimation, for example. So on each of these plots, there's a number printed on it. So here the width of the stellar locus is 15.48 millimags. And this metric gets dispatched to Sasquatch, which is our observatory service for recording and displaying telemetry data and science quality metrics. This lets you correlate the two. So this is the width of the stellar locus as a function of time. In this case, which is a proxy of pipeline version because it's running on a fixed curated data set called HSC RC2, which I'll go into in a second. Not all the metrics have plots along with them or in analysis tools. So a couple in the algorithms workshop, for example, we explained how in HSC data, after flat fielding, there was a offset in the background from amp to amp. And we have been mitigating this using Panstar's continuity algorithm. In the last year, Irfan generalized this to any camera geometry, and we now dispatch the offsets that have been applied to the amps to Sasquatch to use as either a camera diagnostic tool or a ISR diagnostic tool. If both are going great, then the offsets that are applied should be very, very close to zero. Okay, a little bit more about that curated RC2 dataset that I showed in the previous slide. For years, we've been running pipelines on these curated datasets as a way to assess pipeline performance. We run hundreds of square degrees on an annual cadence. These a data set that you're going to see frequently in this talk is the HyperSuPrimeCam Public Data Release 2. NAOJ has made a number of public data releases using the science pipelines, and I think I saw Furusawa-san here today. If you want an independent opinion on what it's like to make a data release with the science pipelines, I'm sure he would love to talk to you about it. They have graciously let us keep a copy of Public Data Release 2 at the USDF, which we use for both scalability tests and robustness tests of the pipelines. And you'll see some plots of PDR2 data later in this talk. The RC2 data set I showed you earlier along with the DC2 TestMed1 dataset, are both approximately 5 square degrees of curated data from both cameras. That is the minimum data set you need to assess pipeline performance and decide whether you want to turn a config parameter on and off or swap an algorithm in and out. And you're not going to see any plots from a 1 degree size data set, but just know that we run smaller set nightly to maintain pipeline health and alert us if there's bugs very quickly. Okay, so that's what happens if you keep your images fixed and vary your pipelines. But you can also use the same scientific performance tasks to assess image quality. If you hold your pipelines fixed and vary your images, you can still, for example, measure the stellar locus and get different values for each of your data sets. So these range anywhere between 22 millimags or 9 millimags, depending on the data set that you're running on. And so we are practicing using the pipelines in this mode during commissioning by running on the real-time data sets that have been streaming off the observatory over the past couple of years. So I'm going to go through those 2 data sets and then the 3 pipelines that we run in real time on those next. First data set is Lattice, where we've been on Sky with Lattice every weeknight that it's been possible. This screenshot is from Rubin TV, and you can see printed on it the number of observations that were taken with Lattice in that particular night. There's the hole in June is because it's winter there and they've had some snowstorms and bad weather lately. The newest real-time data set that we've been running the pipelines on is simulated ComCam data. So we simulated a bunch of ComCam data, and you can set ComCam to emulator mode, wherein it can play back images as if you're observing with ComCam live. And we ran this over the course of a handful of operations rehearsals. We refer to these as OR3 or OR4 in the rest of the talk. And this let us practice our 24-hour communication cycles that we expect during commissioning and make sure that we have the QA scientific performance plot coverage that we want. And this has been super useful for us, of course. Now, the pipelines that we run on these 3 real-time data sets are the quick look pipeline. So this supports the observers at the summit, and by giving them real-time feedback. There's a row for every observation taken. We have image monitors, focal plane plots, and the newest is an interactive tool that lets you plot any quantity reported on these images versus any other quantity. This is still in beta testing at the USDF and the summit. The nightly validation pipeline is data release flavored, and it summarizes last night's data quality to support the summit and scheduler decisions for tonight. You can think of this as a night report. So this plot, for example, shows the photometric repeatability from the 3 nights in Ops Rehearsal 3 versus the 3 nights in Ops Rehearsal 4. And you can see there's a big difference in the photometric repeatability. This is just because we decided that running the global calibration task is overkill for a night report. But you can see that it does make a big difference. And then, oh yeah, and I'll also say, you're going to hear us refer to a tract a lot. This is just how we tile the sky. A small region of the sky that's a little bit smaller than a focal plane is what we call a tract. And finally, the alert production pipeline that we will be running in operations has been running nightly on Lattice data since 2023. It's still going strong, and Sinbong's going to tell you more about that.
Okay, so I'll give a quick update about prompt processing, which is the framework that runs this alert production that will produce the data product within 120 seconds after the shutter closes. So I know Yusra just mentioned it, but I will repeat because that's the key takeaway that I want you to have. It's like we have been doing this in operation for more than a year now. Last March, we put this we deployed this in production. And ever since, whenever somebody take on sky imaging data, they are automatically transferred to USDF and trigger the processing. And then we exercise the framework's workflow and then do all the downstream alert production. So, so that doesn't mean we are idle. Actually, we are busier than ever because all these operations actually help us to actually learn from the operations and know and then we do more development based on the experience we learn. So we exercise this workflow with two kinds of data: the lattice data from Oxtail, and also this year the simulated ComCam data from OR3 and OR4. So on the right plot over there is the timing plot from the OR4 a month ago. 0 is when the exposure ends for each exposure, and then relative timing is shown on the pink spread. Over on the right is when the data outputs are written. So you could see that the latency is higher than we want them to be right now, but the team is working very hard at every aspect of it to make the latency shorter, and hopefully we can meet the requirement. And besides the data products, we also write the metrics to Sasquatch for monitoring. And also we updated the APDB. And in OR4, we send the alerts, and those alerts were received by 4 brokers downstream. And in the last year, we also work a lot on the monitoring and reporting side of the thing. So here I'm just showing you some screenshots of our Grafana dashboard and chronograph dashboard and the time square notebooks. So we've been developing tools and dashboards so to be able to do the operation a bit easier. So now you have learned a lot about, you heard about the data sets that we do processing on regularly and the campaign we run the processing on. So next we will look through each of the algorithms and tell you a little bit about how the algorithm is performing right now and what's new since last year and what we are planning to do in the next year to come. And the first one would be Bruno, who's joining us from online, and he'll talk about image differencing. So Bruno,
Hi.
are you there?
Yes. Can you hear me?
Yes.
Great. Okay, so I'm going to talk a bit about image differencing in the stack. So since the last year, we've been running with the refactored code base. This is from version 23 onwards, which enabled subtractions with different flavors. This is what we call the default, the auto-convolution, and the pre-convolution modes. And this enables the pipelines to work agnostically in terms of the PSF size ratio between the template and the science images. We have conducted different tests on the efficiency and the performance of these flavors in October 2023. So you can see here in this plot, this is the efficiency of detecting transients as a function of their signal-to-noise ratio for the 3 flavors. Still, the efficiency looks good. I mean, in terms of the value of the metric, but we still have some issues. In next slide, I'm also showing you the fluxball distribution. Next slide, please. Of the photometry results for these fakes in HSC precursor dataset, and many other tests were conducted, and you can read about them in DMTN 256, which is the link over there. Additionally, the pipelines were using the fake injection framework, and many tasks were becoming a bit of an obstacle for developing new assessments. So in the next slide, I'm going to show you a bit what it's currently in the DI pipelines. We have strict detection and masking that happens now on runtime during difference imaging. We have rejection of DI sources that have central pixels masked in different mask planes of the images. Also, we have now a deblending routine of DI source footprints. More improvements are going to come on these, specifically for dipoles. And then lastly, the fake framework that I talked about in the previous slides, it's all refactored and uses now the source injection package from LSST stack. So this is deprecating all fake specific processing tasks that were outdated and Now it's made the code more reliable, and it shares a lot of the code base with DRP. So additionally, this enables specific fake catalog design for diverse science cases, testing supernovae or different object light curves. It's also compatible with calibrate image, which is a technicality, but it's a big improvement for us. So in the next slide, I'm showing you a few tests that were conducted using fake sources in HSC precursor dataset. I'm showing you in the left some cutouts of sources of different signal to noise ratio, 10 on the top, 18 on the bottom. And then the photometric residuals that we get between the fake magnitude and the PSF magnitude of the different sources in GNR filters. So this is looking very well, very good for us. In the next slide, I'm also showing you the flux fold distribution. This is the flux differences weighted by its reported errors. And then showing you the astrometric matching of these fake sources in the DIA pipeline. So clearly we're working very well. This is on the left on arc seconds, on the center, on the right in pixels. And then finally, a new efficiency estimation of the pipelines. So this is again only on HSC data, but it's looking very, very good. We have now a better stats on the fakes to measure the 50% efficiency signal to noise ratio. This is the value quoted at the bottom, 4.2, which is very good. Finally, what's next on difference imaging? Oh, sorry. I forgot. We have also tested the pipelines with real data. This is done by people that work. Well, we've been working in the DECAD survey. Thanks to Bob Armstrong, we have these beautiful light curves from real transients processed on DECAM images. Also, there you can have the pipeline of the survey for checking the paper of the survey. Now, yes, on the final slide for what's next, we've been working a lot into investigating strategies. We're going to work on mitigating template PSF discontinuity effects for subtraction, which is a key element for year 1 and year 2 and early science in LSST. So additionally, I'm showing you new plots and metrics that are able to quantify our performance. For instance, a map of this science PSF size on the center, a template PSF size. And then on the right, I'm showing you the kernel matching of DIA centroid offset, which is key elements to study these. And with that, that's all for DIA. Thanks. I'm leaving you with Eli to talk about ISR.
Hi there, I'm Eli Rykoff. First slides, I'm talking on behalf of Chris Waters and Agnes and others in the instrument signature removal. And here's Oxtel without 2D overscan, and on the right with 2D overscan, and there's some Ware patterns from the compression, but it does a lot better. This is an ITL sensor. This is one of our worst ITL sensors. And a little warning, ComCam has 9 of our other worst ITL sensors. We saved the best ones for the real camera. Best estimate is that, about 5% of the detectors on the LSST cam will require this sort of treatment. So where we've been, calibration production, making bias darks, the photon transfer curves, all of that has been done largely ad hoc. If you see new defects, then, Chris, someone else comes, put things together and uploads them to the summit. But we've now stood up the Telescope and Auxiliary Instrumentation Calibration Acceptance Board, or TaxiCab. And this is my name. It has made other people annoyed, but this is going to be my lasting contribution to Rubin. And we gather people from outside of the calibration team, different cameras, instruments, to look at the calibration quality metrics and agree that these should be the default calibrations. We have a standing blocked off meeting every week that we don't always spend, but when we need to, and we'll probably have more common meetings during early commissioning. And this makes sure that a wide variety of people are aware of things that are changing and making these decisions. And the recent operation rehearsals, including the calibration rehearsal, demonstrated that not just us and the direct team are able to run these pipelines. So we're trying to automate as much of this verification process as possible. We've had these CP verify, that's calibration, production, verify pipelines that measure metrics. They didn't really go anywhere. We now are integrated with analysis tools, so we can upgrade to those handy Sasquatch things that Yusra showed. It's still not quite done, but we will have, on the metric dashboard, the read noise of amp C00 on this detector is a function of time every day. So that's the goal, and we're getting close there. And we have, through the OR, the first taxi cab report being generated with drill down metrics so that we can view them. The old system was based on IPython notebooks, which were not as flexible. And here's an example. And this is, I guess I edited after. This is ComCam sim data. This is simulated ComCam data. This is one of the read noise and the bias per amplifier. And it'll be much bigger with much smaller amplifiers when we have full LSST cam. But this is all what we simulated to have realistic variations in read noise. Where we're going, we're currently testing and debugging a brand new instrument signature removal task, ISR task LSST, based on a fun model of what we understand functionally of our readout chain and where all the crosstalk and nonlinearities are coming from. And here's a flow chart of all the steps that we're doing. And Agnes and myself and Alex are working on getting all these parts in. And it's a separate task. It's going to be called something else because we don't want to put all the if-thens in that would require complicated comparisons to HSC, but it's all based on the same building blocks. So all of these little functions are the same. It's just the ordering. And now on to photometric calibration from ISR. The next step is to get a uniform photometric calibration over the full survey. And for this, we're using the Forward Global Calibration Method, FGCM, from Dave Burke, who recently retired from Slack, and myself, developed for DES. This is a forward model of the atmosphere and the instrumental throughput using ModTran for the atmosphere. Here's our standard atmosphere. It's a finite number of parameters, ozone, Rayleigh scattering based on the air mass, aerosols, water vapor. And this varies over time and with air mass, but we can fit the atmospheric parameters from the stars over a wide range of colors and air masses as we observe. And we can also make use of auxiliary inputs such as the Oxtel spectroscopic modeling, though that is not going to be part of the fit right away. How well does it work? Well, DES was a multi-band survey with multiple dithered passes, like LSST, except much less so. If you want to see the standard stars, here's the paper. Recently, we've made more detailed comparisons between DES, Pan-STARRS, SkyMapper, Gaia XP. On the left is DES G-band versus Pan-STARRS 1 G-band, and all of this modeling is part of the Pan-STARRS tiling. This is still consistent at the 3-4 millimag level in terms of uniformity, but DES we did very well. On the right is versus Gaia XP, and you can see lines of ecliptic, constant ecliptic, which are the Gaia scan pattern. We've also run FGCM on HSC data, and Tris right here, Tris can raise your hand, is making the all-sky metric plots, which show the repeatability per tract in the R band. And there are a couple regions where I'm not quite sure. I have to dig in. This is new plot, hopefully with new proper projections in the future. Another big change that we've made recently is these compensated top hat filters. This is just fancy local background subtraction. And the problem is our standard that we had been using of large apertures had significant background biases this is significant at the 0.5% to percent level, but we care about that. After implementing this, we had hoped to use Gaussians. That didn't work. I can talk about that. But the repeatability metrics in the stellar locus, or the repeatability metrics in the stellar locus all improved with this change in the HSC RC2 data set, as well as Lattice and ComCam sim data. So we're preparing for commissioning with ComCam and LSST Cam. FGCM should work with LSST Cam out of the box in a few weeks. We got it working with ComCam sim in less than 2 weeks. I'll show you QE scans and filter scans for LSST Cam. One of the fortunate things is that on LSST, the lens, detector, filter all co-rotate. So the spatial variations are much easier to model than HSC, where the filter did not rotate with the rest of the camera. Now, fortunately, the special survey program chose one orientation, so that wasn't a problem. But there are additional HSC observations with rotations, and flat fields are very difficult when they vary with rotation. So you just have to eat that at the moment. I want to note precision photometric calibration of ComCam will be challenging. Now, it's not the point of ComCam. ComCam is here to commission the observatory and the telescope, not necessarily ComCam itself. We don't have good QE scans or filter scans for ComCam. The collimated beam projector, which I'm not going to talk in detail, will not be ready in time for our ComCam observations. So we will not have that. Just as a taste of what we have to deal with for the instrumental calibration for LSST Cam, we have 2 flavors of detectors, ITL on the outside and E2V in the middle. And on the left is the relative G-band transmission. They have different integrated transmission, but this comes out in the flat field. This part is easy. On the right is the chromatic term. If you took 2 stars of the same magnitude, one very red and one blue, and put them on one of the blue detectors, and then dithered the telescope to one of the red detectors, they would shift relative to each other by 2.5%. So we have to understand this from scans. Fortunately, we have QE scans from the lab, from SLAC, and from Brookhaven, and we're going to also have the collimated beam projector, hopefully in time for LSST Cam to measure in situ. That's the detector part. I can show you all the bands. For the filters, this is another shape. This is nominal detector throughput, looking at the R-band filter variations. And there's radial and azimuth, and you can see the vignetting. That's the sudden change when the beam actually hits the edge of the filter. And there's some radial dependence in the filter edges, and that's what creates this percent level effect. So this is not tens of percent, but our goal is to get under 0.5% in all of these, so we have to understand it. And now I have Pierre-François.
Hello, I'm Pierre-François, and I'm working on point spread function modeling. And so back in the day for the pipeline, to model the point spread function, PSFX was used. But when you were using it on a precursor dataset such as HSC, and you were projecting PSF residuals across the skies. So here, this is a PSF size in different filters. You can see like some structured, like spatial correlation of PSF residuals, and that this is something you don't like for doing cosmology. And so it was an issue. And if I was not there when it was done, but if I understood what happened, it was like a problem of 2 good nights where like the quality of the sky was amazing. And so like the stars used for fitting the PSF were undersampled, and PSFX in its configuration at that time had a trouble to fit the PSF, and this is what you are observing. But we moved on, and we implemented a new PSF model, which is coming from PIF, where PIF is a tool that was developed within the dark energy survey for measuring the point spread function for cosmic shear analysis. And when PIF was implemented into the pipeline, in the case of Subaru, it removed like this kind of huge structure in the sky. So this is so much better. And this is kind of where we are now in terms of PSF modeling for with the Rubin pipeline. And so in what direction we are going now? So there is a first work that will be done, that is currently done, purely on software, because like PIF right now, if you want to fit the point spread function on a single CCD, for example, on Subaru, it takes about like 30 seconds to fit one CCD. And in terms of the amount of data that we will have to process with LSST, this is kind of too slow. So there is an ongoing effort to make it faster. And there is a second task that we will work on, which is like more on the physical side of modeling the point spread function, which is like we know that the PSF has a chromaticity dependency. And also like we know that DES has implemented a color correction between year 3 and year 6 into PIF. And that adding this correction helped to improve PSF modeling. And if you have any question about that, you can ask CO that implemented this correction. And the idea is to implement this exact same correction at the first order as in DES, which is like just a linear color interpolation in addition of the spatial interpolation. And it will be like the first iteration to implement chromaticity into the point spread function as the first approximation. And oh yes.
All right. So I'm Jim Bosch. I'm speaking for, I think, mostly Arun Kanawati in this part here. So our plan for shear estimation is very much taken from the dark energy survey, where some of our colleagues, Aaron Sheldon and Matt Becker in particular, we're also members of the Dark Energy Science Collaboration, have put together a prototype based on what they did for DES that they've tested on some LSST data, and we're basically planning to adopt that prototype. But the first step of that is building coads. And so we've, I think, sort of along with them developed this approach to building coads in small cells where we can really control what the PSF is. And there's about 250 by 250 pixels. That's about half an arc minute, maybe a little more than half an arc minute. And so each cell in that coad has a constant, or approximately constant PSF, because the PSF doesn't vary that quickly on a coad with many images going into it. And because we can control exactly how many epochs go into that, we can throw away things that are have too much of an edge in them. We can make sure that the PSF doesn't change discontinuously in the coad, which otherwise could be a big problem. So this is something we have to integrate very tightly with the rest of our code, unlike the shear code that they've provided, which we can probably just run. And so we've been spending a lot of time in upgrading our coad building software. We want to take advantage of some of the things they've added on the DES prototype to control the PSF quality and do noise propagation. We also want to keep some things we've had in our coad pipelines for a long time in terms of a more efficient structure for how we handle overlaps and warping. And also our approach to detecting artifacts like ghosts and satellite trails, which I think is really sort of the state of the art right now. Nobody else can detect garbage in coads to the same extent we can. Next slide, please. So here's some examples. This is a cell-based coad on the left here. You can't actually see the discontinuities because they're on average so small, and they're discontinuities in the PSF. So most of the pixels are noise. You don't see discontinuities in the noise really, unless they're really dramatic, and there just aren't any dramatic ones here. So that emphasizes that even though this is a cell-based coad, like the fact that it's in cells won't disturb anybody who doesn't care about those cells. Like it just looks like a regular coad to everyone else. And this is important because we are planning to use these cell-based coads for all of our object table measurements. We may or may not use them for the image subtraction templates. But this is how we're going to do all of our deep measurements on these cell-based coads. And part of that's going to, for anyone who's used our pipeline recently, this is going to be a massive speed up in how fast we process coads. It's going to solve a big computational performance problem as well. On the right here, you can see the cells. We actually build these cells with overlaps within them. So you can see these are all adjacent cells. You can see the same galaxies in different cases. And you can see here, it's maybe not totally intuitive from how this is laid out, but the same objects appear in multiple ones that are adjacent because we actually build overlap regions into those cells. Now, in the image on the left, we've thrown away all those overlaps so you can get a nice stitched together coad. But we do actually keep those overlap regions. So if you want to do something in terms of like convolve the image, we've got extra padded regions that you can use for those convolutions in order to be able to do the right thing on the inner regions that are unique. Next slide. So what's next is after we've got these cell-based coads in place, and they're very close, they're not integrated with the pipeline yet, but we can build them in sort of a separate branch of the pipelines. The remaining steps, I think, will basically be done with that desk developed code. And the main challenge at this point is going to be change control and testing, because we're working very closely with desk people who work on this code. And while that code isn't changing a whole lot, we are integrating into our pipelines. We want to make sure that the testing they've already done isn't invalidated by changes we make. So we have to get our own testing regime up in place. We need to have ways to make sure that we're not making arbitrary changes, but we are making the changes that we need for the integration, and that those don't disturb those don't invalidate the testing that desk people have already done. And this is going to be especially important during commissioning when things are just evolving really rapidly. All right, next slide. All right, going on, I think I'm going to be talking to these galaxy photometry slides as well. So this is specifically galaxy fitting. We have different approaches for galaxy colors that involve the more sort of PSF match style photometry. But this, a lot of our premier galaxy measurements come from fitting galaxy models after involving them with the PSF. So we've long had this C model algorithm that I developed years and years and years ago. It's been used for HSC. It was inspired by something for SDSS, and it's just not a very good model. Nobody believes it's actually what galaxies look like. But it's done well enough. And Dan Turano has been working for a long time on a replacement to fit more physically motivated models. And if you can go to the next slide, you can see how this same plot of the C model minus the reference, this is on a simulation, how everything sort of tightens up. The photometric scatter goes down. It's hard to judge how things go with simulations of galaxies because it's really hard to simulate realistic galaxy profiles to begin with. But I think this is really doing quite well now. For a long time, this new algorithm struggled with performance in terms of being as fast as C model. C model is, as Robert Lupton would say, sleazy, and that's why it can go very fast. It makes some serious approximations. And these algorithms don't make those same approximations. They make much more reasonable and clever approximations. They use mixtures of Gaussians to evaluate the galaxy and convolve with the PSF, and it's now competitive at speed. So we're working very hard to get this integrated into the full pipeline, and we're really looking forward to this being where our new galaxy photometry measurements mostly come from. All right, next slide. All right, so here's just sort of the status. So we're definitely planning to finish integrating these new codes into part of the multi-profit package that Dan's been working on before commissioning. The cell-based coads will make this a little bit better in terms. They probably won't matter much for the quality of the measurements, but they will matter immensely for making this go fast, as I mentioned before. There's some chance that we could look into doing another round of linear deblending. And essentially, we fit all the models to the blended data. And then once we've got those models for a number of objects that are blended together, we can fit just the amplitudes of those galaxy models while still convolving them with the PSF. And that's been promising, but it's something we have to investigate more. We want to get the baseline version in first. Dan also is the head of the Galaxy Photometry and Photo-Z Commissioning Science Unit. So they're working on putting together metrics to characterize how we're doing. It's actually a very tricky thing to characterize how well you're doing for galaxy photometry on real data. A lot of what we've done so far has been on simulations because you just don't have anything like truth the way you do for simulations, and it's enough is uncertain about galaxies, you can't just see them as point sources, that it's hard to construct metrics. So this is very important work to figure out, how to characterize how well we're doing. And I think that's it.
Thank you, Jim. Another algorithm where DES has been pushing the state of the art is astrometric calibration. We've adopted Gary Bernstein's astrometric package, which we have affectionately named the GBDES. We use the Gaia DR3 as the astrometric reference catalog. This algorithm fits proper motion and parallax. This plot shows the astrometric repeatability metric. We call it AM1 in the science requirements document for the Z band. And with this HSC public data release 2 dataset, every region of the sky is performing better than the design goal of 10 milliarc seconds. And many regions of the sky are performing better than the stretch goal of 5 milliarc seconds. And of course, we think we can do even better. This past year, we have focused on the getting ready for commissioning, where we expect to have the data that is not necessarily the best quality. So there's now a mode in which you can fit all the images from a survey together, not just the ones that overlap a particular region of the sky. You can fit all the bands together, which provides more constraints with less data. And now you can use the camera model that's output from GBDES to fit new data. That is current work in progress, is using those models that are output from GBDES in single frame processing to improve the astrometric fits in alert production, for example. We also have a prototype of differential chromatic refraction fitting that works on operations rehearsal 4 data. Here's some examples from Claire's fitting, where she shows that one DCR constant is sufficient. And we're also prototyping, modeling the atmospheric turbulence with Gaussian processes. Detection and blending the status has not changed a whole lot since I spoke to you a year ago. Public data release 4 of HSC is using Scarlet Light for deblending. So remember, Scarlet was developed for fitting data from multiple cameras together. If you dial the number of cameras down to just 1 pixel scale, you can use analytic gradients, which greatly reduce the memory usage and the runtime. This is what we call Scarlet Light. They are for one pixel grid, they're essentially the same algorithm. This Scarlet Light very comfortably fits within our compute budget now, and we are not worried about that at all. This upcoming year, we're going to spend some time working on detection, specifically creating multi-band coad or multi-band detection algorithms that use all the bands at once, and also working to make Scarlet Light more robust in crowded fields. And the last algorithm today, solar system linking. A year ago, we shared that the best demonstration of this algorithm's performance was when it detected a real near-Earth asteroid in archival ATLAS data. This was not a recovery of a known asteroid. This was discovery of a new one that the ATLAS pipeline missed because it depended on having 3 good observations in a single night to make a track. For this particular asteroid, one of those, it was observed over the course of 4 nights, but every night, one of those 3 observations was bad for some reason. HelioLink, the algorithm that we're using in the pipelines, is able to link multiple nights together, just like we planned to for LSST, and was able to recover this asteroid. ARI reports that on DP 0.3 data, estimates of completeness of this algorithm are 99.85% completeness. This upcoming year, we're going to focus on taking this algorithm and then wrapping it as a pipe task so that we can run it with our middleware and integrate it in with the rest of the pipelines. And of course, this is a theme that you've heard from many of the speakers today. We're getting ready for commissioning this upcoming year. So while we've done everything that we can do with precursor data, there are simply some unknowns with the system that you can't measure until you have hooked everything up and are on the real system. We have to do things like tune config parameters, build illumination corrections, build camera distortion models, and these measurements we can't make until we have the real system set up. So this activity is what we've referred to as pipeline commissioning. And the solar system algorithm is no different. We expect to have to do some configuration tuning once we're on Sky with LSST Cam. And that takes me to our wrap up. So many of the Science Pipelines team members that you've heard from today and put work into these slides are also members of the commissioning science units. And when we're in commissioning, they will be responsible not only for verifying requirements associated with the algorithm that we're responsible for, but they're also going to be responsible for these Science Pipelines commissioning activities as well. And this is going to be a very busy time for all of us. Tomorrow, there's going to be a session at 10:30 led by Keith on commissioning. If you are interested in helping out during the commissioning process, I encourage you to come to that session. We'll talk a little bit more about what's involved with pipelines commissioning and how you can help out. Yeah, I will leave it there. So finally, we are very proud of the pipeline performance on precursor data. We of course know we can do better. And we're really, really excited to give them a whirl on LSST Cam data. It's going to be a busy time. And if everything goes well, when we give this talk next year, it will have plots from LSST Cam data. Can't wait. Thank you. And okay, and now we're going to transition to the panel discussion phase of the session where we'll take questions and try to direct them to folks who can best answer them. Yeah, raise your hands and Sid or Theo will bring you a microphone. I did mean questions. I meant, yes, I meant ask a question and then we will jointly answer it.
This is just a small clarification question on that asteroid that was found at the PHA. If you can go back to that slide, a few slides back. I just wanted to understand what all the many points that we were seeing in that plot were. Whoops, you went way back. One of the very last figures that we saw in the whole slide deck.
I know there's a delay. Be patient.
Yes, that one. It was there for a second. I was just wondering, so we're connecting 4 dots out of looks like 10 to the 4 dots. What is the problem as impossible as it looks visually, or how should we try to understand this figure? That is, what are all those many colored dots on this plot?
Yeah.
I think there are DIA sources that are not matched to any static object. And you are right, getting few dots picked out of many dots is a traditionally hard computational problem, but HelioLink solves it by and large. If Ari is online, he could add you more detail.
Yeah, but I was going to answer where the dots came from. There are problems in the CCDs mostly. So those are, you can see the edges and things like that. So it's a lot of spurious detections and probably some real ones. And as Mario, the other one, Jelko says, the clever thing about HelioLink is pulling the real orbit out of all those detections. Those are all nominal detections. made on 4 different nights.
I think it's worth mentioning that I believe that these detections are from the Atlas pipelines. The HelioLink algorithm being run is the Rubin algorithm, but this is not Rubin image subtraction.
This is just a clarifying question, since I'm not an expert on cell-based quads by any means. How does cell-based quads decide which of the various quads that include the same objects is the one that gets kept? Is there a metric for just the one that's closest to
So to clarify, you're asking, when we make the cell-based coads with the overlaps that coad the same, pixels multiple times, maybe with slightly different epochs contributing, how do we resolve those duplicates? Is that right?
Yeah, how do you decide which one to keep?
So for most of our processing, we're actually going to strip off those overlap regions and use them for sort of convolving the image and deconvolving the image to the extent that we have to do that for processing. For instance, when we detect, we convolve by the PSF. So we'll use those overlap regions to convolve, but then we'll stitch them back together after we've convolved. And that means we'll just naturally build one catalog that has, that doesn't have to worry about those overlap regions at all. A lot of our processing will then not actually care about those discontinuities. It's only a few of our algorithms that care about those discontinuities in the PSFs enough to go back to the original cells, either by looking at the overlap regions, which is what the metadetect code will do, or by essentially rendering PSF convolved models separately in the 2 different cells and stitching them together. So only in the case where you're processing the cells independently and redetecting on those cells do you have to worry about the matching problem. And metadetect will have that matching problem. And they've got some heuristics for, basically spatial matching kind of things where you throw away whichever one is, you have some heuristic for which one you throw away. I'm actually not familiar exactly what they're doing, but it's, I think, basically exactly what was done on DES. But most of the time you won't have that problem.
So looking at that figure, what I'm taking out is that the overlap regions are fairly large. So there's only one region in which it's primary, and the rest are all overlap regions. Gotcha. Thank you.
I just wanted to add the cells are pre-decided. Like there's a cell tiling on the sky that you could look up right now. So you just, and then what goes into that cell is whatever images fully overlap it.
Siegfried has a question on Zoom, so please pick up now.
Yeah, thanks for the great session. It was really very informative. This question is probably for Bruno. When I look at the graphs in slide 31, it seems to me, if I understand correctly, and I just want to clarify that at SNR5, we only, diff imaging only picks up 4 of 5 objects. Is that right? Or what
Sorry,
is the
yes.
efficiency here? Yeah.
So this is with the old fixed framework, and we were having issues with increasing the stats. So clearly we have few sources. So you were saying that at signal to noise ratio 5, we were picking a few. Yeah, we had issues with raising up the stats in the old framework. But now this is trivially solved by the new framework in which we can have more stats. I think that's basically what's going on with this particular plot. I agree it's not the most beautiful plot of all.
Okay, so this is solved. Do I understand it correctly?
Yeah, this is actually where we've been in the previous versions, and if you go to the next 2 slides, then you'll see what's actually the next one, I think. Or this, the next one. That's the current figure that we are looking at.
Okay, I'm still a little confused. Sorry about that, but it seems to me that at SNR5 there's still an efficiency of 80% or so. Is that correct? Is that the right graph?
Oh yeah, that's probably, yeah, that's right. Yes.
Okay, thanks.
This is, yeah, just for clarification, this is an estimation of the SNR. So the real estimation of the signal to noise ratio when we are dealing with fakes is a bit more complicated than just the simple photometry. So that's also one caveat. This is merely a proxy. And the detection in the pipelines, usually the threshold is around 5.5, it depends. But that's another technicality. We can discuss further if you have more questions.
Thanks, Bruno. Much appreciated.
Have a follow-up question. So I actually was going to ask the same. And so looking at the specification of the alerts, and it says 90% complete at signal to noise ratio of 6. That looks like it's correct. And but there's also 95% purity. Do you have an estimate of the best guess of what we will achieve?
Francisco, I can take that. We don't have a recent quantification of that, but I will say that those requirements are on the real bogus classifier. They're not on detection itself. The completeness curve you're seeing here is reflecting the intrinsic statistics of detection. So the requirements are levied on the classifier.
Hi, I was wondering if you could expand on Scarlet Light and how much faster it is, and what the costs are in terms of like photometric performance.
The question is, what was the runtime improvement and the memory usage improvement?
Well, I just remember that Scarlet was really quite slow, and now you tell me it's a heck of a lot faster. I'm just wondering how much faster, like that 10 or 5 or is there a...
It was order of magnitude order. I would have to dig up my slides from last year where we reported the exact numbers that we got the improvement in runtime and speed since that announcement came last year. I'll dig up the numbers for you and let you know.
Okay, I may be using a very old version of Scarlet then.
Wait, you've been...
I might be using a much older version of Scarlet if I'm still getting slowness then.
Okay, so we've got a new standalone package called Scarlet Light, which we've been using. If that's the package that you're using and you're still seeing some slowness there, we would love to hear about it.
I thought just learned about Scarlet Light today. It's my problem.
Exactly. Yeah. So the like full Scarlet, we know that's slow already. Scarlet Light, we believe we are seeing evidence that it fits within LSST's compute budget. If you see evidence otherwise, we would love to hear about it so that we can fix it. Yes.
Hi, I have heard through the DM grapevine that the documentation site is going to be given an overhaul or a rewrite or an update. Is that true? And what are the plans there? What's the timeline and what types of changes are being implemented? Thanks.
Jim, do you want to take that one?
Yeah, Jonathan Sig is working on it right now. He's our docs guru. I know they hope to get that done quickly, or at least they hope to get it done quickly as of a few weeks ago. I suspect the timeline is sort of around the end of the summer. That will improve the styling and some of the formatting and stuff, but there's going to be a lot of real work to go and then sort of clean it up in that new form too, in terms of adapting the content. And we've long had a lot of content that is not super that has rotted a bit too. There will be a lot of work to actually make the content better. But I think the stylistic cleanup is sort of in the summertime.
That primarily an update to the infrastructure or the content, or is it both? Are they both being done?
it's adopting a new version of the code that builds the docs and lays it out and everything. So it will change how the docs are built. It's the infrastructure and sort of the styling and sort of not a massive change to the organizational structure of the docs themselves, but it is a change to how the structure is represented on the web page.
Last call for questions.
There have been effectively boot camps to try to get people familiar with software. Plans, given the hectic nature of compound.
Okay, so any boot camps that we have from now on are going to be commissioning flavored and with the goal of getting in-kind contributors to commissioning up to speed with pipelines. Tomorrow at Keith's session in the morning, we're going to talk more about how you can get involved and get in touch with your science unit lead and what kinds of meetings we're going to have, what kind of trainings we're going to have. And yeah, we'll spend 20 minutes talking about that question. Thumbs up from Keith in the back. Did you want to say anything more about that now? Okay, if there's no other questions, let's thank all of our speakers. We'll see you at break.